Hello and welcome to this second video in our little series here. I hope everyone is doing reasonably well out there. I, for my part, have managed to not quite lose my mind just yet. As you can see, the topic for today is integration by u-substitution. As you can also see, I have somehow managed to figure out how to put text into these things. I've actually learned quite a bit about using Procreate. Although a lot remains to be learned. Hopefully the quality of these things is going to improve and the number of annoying mistakes is going to decrease as we go along. For now, you're going to have to bear with me, though. In particular, I still have no idea why randomly the pen switches to an eraser on me. You can see over here this little toggly thing. About, 20,000 times during this video, you're going to see that just randomly shift to the middle. And when that happens, I lose the pen. It stops drawing. It becomes an eraser. And then I have to go up here and change the color. I can't click on the same color or else it doesn't switch back. And then I have to start drawing in a new color. So we're going to be changing colors constantly throughout this thing. And I know that's probably super, super annoying. I promise you it is much more annoying for me. So I appreciate your continued patience with that. But nevertheless, we're going to forge ahead and talk about integration by u-substitution. So, okay. In the last video, we talked about the fundamental theorem of calculus. We saw that in particular, that's a bit nicer. If I want to look at the integral from a to b of f of x dx, so the area under the curve of our nice continuous function f from a to b, this is actually going to be capital F of b minus capital F of a, where capital F is any antiderivative of little f. The fundamental theorem of calculus shows us that there's this very deep, very important, very useful connection between differentiation and integration that we're going to exploit to actually be able to compute definite integrals. And so it shouldn't come as a surprise that whenever we introduce a new technique of integration, as we're doing today, we're going to be working backwards from one of our techniques of differentiation. And the first one that you typically learn about in a calculus course is u-substitution, which is working backwards from the chain rule. So what does the chain rule say? Let's just review briefly. Well, the chain rule says that if I have, why is that rule? There we go. If I have two nice continuous functions, f of g, I can form their composite function, h, which is f composed of g. That's what the little circle thing means. What does this mean? This means that h of x is equal to f of g of x. So h is the function that takes in an x and plugs that x into g, and then plugs whatever comes out of g into f, and then what then comes out of f, that is the value, the output of h. And what does the chain rule tell us? It tells us that if we want to take the derivative of h, so h prime of x, this is going to be equal to f prime of g of x times g prime of x. So f prime evaluated at g of x, and then I have to multiply by this g prime of x. And in particular, this is going to allow us to integrate a special class of functions. Whenever I see something like this, whenever I see some function of a function, so I have like an interior function here, and then I have this factor of the derivative of that interior function, that's a good candidate for u-substitution. And so we're going to see how we go about this. Let me roll this back a little bit. First, I think it's a good idea to start off with an example to motivate, a really simple example to motivate what we're doing, and then we'll show the general theorem, the general form of the u-substitution kind of rule, which is going to allow us to handle any case where we have this pattern, this function of a function multiplied by the derivative of the function. And then we're going to stop and we're actually going to analyze this in depth. By the way, this is I'm going to call this a concept video, where we're going to go really, really deep into the idea and theory behind this to get a really, really solid understanding. I know that people want to see examples, and I'm going to do tons of examples. That's what's coming up next. But first, at least, we need to really get a solid conceptual understanding of this. It's very, very important, as in every area of math, to really understand what's going on. And so we're gonna take a little bit more time than, and it's kind of an understatement, we're going to take a little bit more time than usual to really get what's going on here. That's not to say we won't still be hand-wavy. We're going to be very hand-wavy, but we're going to develop a really solid sort of intuition about this. Okay, so first example, if I want to do the integral from negative pi over 4 to pi over 4 of sine to the power of 4 of x times cosine of x dx. This is a prime candidate for u-substitution. And why is that? I can set, and I'm just going to start doing it and then explain it as I go. I'm going to set u is equal to sine of x and du equal to cosine of x dx. And where does this come from? This comes from the relationship d, and just as promised, I've lost the thing. It's an eraser now, and I have to change colors. What should I pick? Maybe blue. I don't think we've done blue yet. Du by dx is equal to cosine of x. This is of course u prime of x. This is the prime notation. This is the Leibniz notation. Since u is sine of x, the derivative of sine is of course cos. And du by dx is then cosine of x. Sorry, I'm kind of losing my train of thought every once in a while here because I see this stupid thing shifting on me. So if I sort of wander off in the middle of a sentence, that's what's going on. Sorry, I'll try to keep that to a minimum. But it is really sort of hard to continue focusing when you know that at any moment the pen could just vanish on you. It's like walking on ice, and you don't really know how thick it is at any particular point. Okay, so after this, I can again, being very hand wavy, think about these infinitesimal things. This du and dx, I can think of this as an infinitesimal change in u, and this du by dx is the ratio of that infinitesimal change in u to the ratio of the infinitesimal change in u to the infinitesimal change in x that caused it, because of course u is a function of x here. And so then I can quote-unquote multiply through by dx to get du is equal to cosine of x dx. And again, hand waviness all over the place, not actually what we're doing, but you can think of it that way. And so this substitution, as we call it, is what allows me to sort of simplify things and see how I can evaluate this integral by anti-differentiating. I can rewrite this thing, and he's gone again. I can rewrite this thing here now as the integral of u to the power of 4 times du. Again, making this substitution, the u is sine and the du is cosine of x dx. But then I'm not going to evaluate this thing from negative pi over 4 to pi over 4. I'm actually going to evaluate it from negative root 2 over 2 to positive root 2 over 2. And this, of course, is because sine of pi over 4, as hopefully we all know, is root 2 over 2, and sine of negative pi over 4 is negative root 2 over 2. So I have to adjust the bounds of integration of this thing, and we're gonna spend a considerable amount of time looking at that and thinking about that. The first thing I'll say, and we're not actually going to evaluate this thing because that's a good exercise for you guys to try at home, and also I'm lazy. This, by the way, this is like the 27,000th time I've done this same video, with all these little kinks being worked out as we go. The last one was almost perfect, and then I found that the sound was off. It was great, but so you guys can take care of the details with that. But we're going to focus on the concepts. Why am I not integrating from negative pi over 4 to pi over 4? Morally, the reason is that here what's changing is x. So I'm multiplying by this dx. We're going to go into a lot of detail on this. For now, I'm just going to say that here the x is changing. So and the x is varying in between negative pi over 4 and pi over 4. Now when I switch to the u, well, it's the u that's changing. I'm multiplying by a du, and when x goes from pi over 4, or negative pi over 4 to pi over 4, the u, since u is sine, sine is going from negative pi over 2 to pi over 2. And that's the adjustment that I have to make. We're going to go, and this, by the way, this is where it's usually kind of left when it's being taught. I was never satisfied with this, and so I kind of sat down and thought about it for a while until it sunk in, and I find that actually sort of a kind of graphical approach really helps it hammer the point home. If you're satisfied with this and don't want to bother going deeper into it, you can absolutely just pause the video and skip ahead to the examples. But for those of you like me, are not quite satisfied with this and want to think about it a little bit more, we have this second layer. I figured out how to deal with these. Whoop, there to go. And I want to get rid of that. I'm very, very proud of myself for figuring out how to do this. I've switched to this second thingy here, and now I'm going to actually want the eraser. Finally, it came in handy. Where we have some graphs. We have the graph of, what's a nice neutral color to sort of talk about these things with. Let's go for putting way too much thought into this. Let's just go for whatever this is. Here I have on the horizontal axis x, and on the vertical axis this f of u of x times u prime of x. This is the u that I'm going to be doing the substitution with. Here I have on the horizontal axis the x, and here the u of x, because u is a function of x after all. And here I have on the horizontal axis u, and on the vertical axis f. And now I'm going to start thinking about the kind of geometric approach to what's going on with u substitutions. So the goal here is to evaluate the integral from a to b of f of u of x times u prime of x dx. And what's that? Well, if I mark my a here and my b here, this is, of course, the area under the curve of the graph of f of u of x times u prime of x in between a and b. And so I think I mentioned in the fundamental theorem video, I should get a different color for this, definitely. Maybe this orange guy here. That we can think of this, and I'll do an entire video on this, on Riemann sums and the theory behind integration. But very hand-wavily, we can think of this as an infinite sum of infinitely thin sort of line segments with infinitesimal width dx and infinitesimal height, actually, sorry, not infinitesimal height, just normal height, and he's gone again, and height, now we'll come back, here we go, and height f of u of x times u prime of x. So we're thinking about, as x goes from a to b, this infinitesimally thin stick thingy is kind of moving along here, and we're summing up all of these infinitesimally thin rectangles, and that's what this notation is telling us. This is telling us that we're going to go from a to b. X is going to vary from a to b, and as we go, we're going to be summing up all these little rectangles with infinitesimal width dx and infinitesimal height f of u of x times u prime of x. And again, this is not actually what's happening. This is very hand wavy. This is actually a limit of Riemann sums, but this is a way that we can think about this for intuition. So that's what's going on down here. What's going on up here? Well, we've done this substitution. I'll write the substitution down in the corner here, and then move back up. So I've noticed that by the chain rule, I have this. Actually, sorry, not even by the chain rule, just my normal differentiation. I know that u prime of x is equal to du by dx, where again I'm thinking of this as an infinitesimal change in u divided by the infinitesimal change in x that caused it. It's actually a limit of difference quotients. we'll do it. I'll do a video on differentiation to clarify this. Although we've already covered that a lot. And then I rearrange this. I multiply with air quotes by the dx, and I end up with du, the infinitesimal in u, the infinitesimal change in u, being equal to u prime of x times dx. And now, keeping in mind that u is a function of x and f is a function of u, I can start going up here, and thinking about sweeping out area by taking an infinite sum of these infinitely thin line segments, or little rectangles, with infinitesimal width du and infinitesimal height f of u. That's the way I'm going to think about this. And this equation here is telling me that I can actually do that. I can actually get the same area that I get down here from this picture if I sum these f of u times du rectangles. But the question is, where am I going to sum them from? My bounds of integration here were a and b, but they're not going to be the same bounds of integration anymore, because we have this kind of u function stuck in the middle here. U is a function of x, and this thing will be the death of me. Okay, so we have this function u of x, and we have x varying between a and b. That's what's happening down here. X was changing from, it was going from a to b. And again, the ghost is changing my pen to an eraser. I don't know why. I can only assume it's a cruel joke by whoever designed this program, which is actually really cool, but also probably the most annoying thing on the face of the planet. So as x goes from a to b, u of x is of course going from u of a, which is here, to I should have extended this thing up a little bit. Should have extended to here. It is varying from u of a to u of b. And so this f over here, this guy is a function of u. So when I think about where I'm summing up my bounds of integration for this new integral in terms of f over here, well, now I'm multiplying by this du. This is my infinitesimal width is now du, not dx. So I have to keep in mind, how is u varying? Down here, I was thinking about how is x changing. And as x changed, I took the height of the function and I multiplied by this dx. Now I'm multiplying by a du. I have to think about how u is changing. And this picture here shows me how u is changing. When x, this x here, for the love of... As this x varies from a to b, well, u is going from u of a to u of b, and so I'm going to mark my bounds of integration over here in this nice magenta color as u of a and u of b. And this is how I get my infinitesimally thin line segment, my rectangle here, varying and sweeping out. I am actually going to... I don't know what I'm going to do. There's nothing I can do. This is one of those things where it's like you want someone to be mad at because it's so annoying, but it's a computer, and yeah. Okay, so I end up with this area, taking this du, this infinitesimally thin. And I'm sorry I'm repeating myself so much. This ghost really is messing with my train of thought here. I'm really going to try to take care of this in future videos. By the way, if any of you are watching this being like, my goodness, this old person is failing at technology, he should just be doing this and the ghost will stop changing his pen to an eraser, please feel free to comment on Piazza, make fun of me all you want, just please do let me know how to get this to stop, because I googled this, and it's a common thing. People are complaining about the thing changing to eraser in the middle of a project, and there were people answering the question saying, oh yeah, this is a common problem. what's going on is you double tapped on the screen and inadvertently changed it, and then they said, "Oh yeah, that's exactly what I was doing. Thank you. I feel so silly about this." I'm actually not tapping the screen at all. I'm not doing anything. I'm just sitting here. I'm not even drawing. I'll just be talking, and I'll see it move, and I kind of wince and think I have to change the pen, and it messes me up. So sorry. This is a huge digression of me just kind of venting about this thing. It's one of the reasons that I've been at this one video all night. So please forgive me. But what were we talking about? Yeah, this area here is going to be the same as this area here, and the reason is this substitution thing here, this du being equal to the u prime of x times dx. And so I end up, instead of integrating from a to b of f of u of x times u prime of x dx, I can actually integrate from u of a to u of b f of u du. And why do I want to do that is a reasonable question. We've gone through all this effort to see why we can do that. But why would I want to do that? Well, the reason is that I had in my pocket the whole time this capital F, this antiderivative of little f, which I now can substitute into here. I can bring this in and say, well, I know from the fundamental theorem of calculus that this definite integral can be evaluated as capital F of u of b minus capital F of u of a. I can actually just stop and solve this thing. And a really good exercise, we'll see this when we do some of the examples, is to do this, evaluate this thing both by, after I've solved for this f thing here, both by just plugging in the bounds, the u of b and the u of a, and also by resubstituting in the original u function and then evaluating from a to b. And we'll see that we do get the same thing. That sounds a little bit abstract now, but when we do examples in the next video, that will become much less mysterious. So I hope this has made things a little bit clearer. And again, sorry about taking a 45-second break to complain about the program I'm using for this thing. I will see you guys in the next video.